In the last video, you learned how a variety of different applications, such as BitTorrent, Skype, and the web, all communicate over the internet using a very similar model, basically a bidirectional, reliable byte stream. It takes a lot of different pieces working together to create this reliable communication model for our applications. But even though we use a huge variety of different internet applications, sending many kinds of data at very different speeds, there are surprisingly strong similarities in the way applications send and receive data. For example, applications want to send and receive data without having to worry about the path or route that the data takes across the internet. And almost all applications want to be confident that their data is correctly received, with any lost or corrupted data automatically retransmitted until it's received correctly. The early internet pioneers created the four-layer internet model to describe the hierarchy of operations that make up the internet, so that applications can reuse the same building blocks over and over again without having to create them from scratch for every new application. Layering is a really important and frequently used concept in networking, and we'll be seeing it many, many times throughout this course. There's even a video devoted just to the concept of layering. Let's look at what each layer of the four-layer internet model does. It helps to remember that all four layers are there to enable applications in the end hosts to communicate reliably. To explain how it works, I'm going to start at the bottom layer. We'll see that each layer has a different responsibility, with each layer building a service on top of the one below, all the way to the top where we have the bidirectional, reliable byte stream communication between applications. Okay, let's start with the link layer. The internet is made up of end hosts, links, and routers. Data is delivered hop by hop over each link in turn. Data is delivered in packets. A packet is a self-contained unit consisting of the data we want to be delivered, along with a header that tells the network where the packet is to be delivered, where it came from, and so on. The link layer's job is to carry the data over one link at a time. You've probably heard of Ethernet and Wi-Fi. These are two examples of different link layers. The next layer up is, for us, the most important layer, the network layer. The network's layer's job is to deliver packets end-to-end across the internet from the source to the destination. A packet is an important building block in the network. A packet is the name we give to that collection of data with a header and header that describes what the data is, where it's going, and where it came from, as we saw in the last slide. You'll often see packets drawn like this. Network layer packets are called datagrams. They consist of some data and a header containing the to and from addresses, just like we put the to and from addresses in a letter. The network hands the datagram to the link layer, telling it to send the datagram over the first link. In other words, the link layer is providing a service to the network layer. Essentially, the link layer is saying, if you give me a datagram to send, I'll transmit it over one link for you. At the other end of the link is a router. The link layer of the router accepts the datagram from the link and hands it up to the network layer inside the router. The network layer on the router examines the destination address of the datagram and is responsible for routing the datagram one hop at a time towards its eventual destination. It does this by sending it to the link layer again to carry it over the next link, which is passed to the network layer at the next router, and so on until it reaches the network layer at the destination eventually. Notice that the network layer does not need to concern itself with how the link layer sends the datagram over each link. In fact, different link layers work in very different ways. Ethernet and Wi-Fi are clearly very different, and we're going to be learning about them in more detail later. This separation of concerns between the network layer and the link layer allows each to focus on its job without worrying about how the other layer works. It also means that a single network layer has a common way to talk to many different link layers by simply handing them datagrams to send. This separation of concerns is made possible by the modularity of each layer and a common, well-defined API to the layer below. In the internet, the network layer is special. When we send packets into the internet, we must use the internet protocol. It is the internet protocol, or IP, that holds the internet together. We'll learn more about the details of IP in later videos, but for now, it's good to know some basic facts about IP. First of all, IP makes a best effort attempt to deliver our datagrams to the other end, but it makes no promises. Second, IP datagrams can get lost. They can be delivered out of order, and they can be corrupted. There are no guarantees. This may come as a surprise. You might be asking, how can the internet work at all when the packets are not guaranteed to be delivered? Well, if an application wants a guarantee that its data will be retransmitted when necessary and will be delivered to the application in order and without corruption, then it needs another protocol running on top of IP. That's the job of the transport layer. The most common transport layer is TCP, or the Transmission Control Protocol. You've probably heard of TCP/IP, which is when an application uses both TCP and IP together. TCP's job is to make sure that the data sent by an application at one end of the internet is correctly delivered in the right order to the application at the other end of the internet. If the network layers drop some datagrams, TCP will transmit them multiple times if need be. If the network layer delivers them out of order, perhaps because two packets follow a different path to their destination, TCP will put the data back into the correct order again. In later videos, you'll learn a lot about TCP and how it works. For now, the main thing you need to remember is that TCP provides a service to an application that guarantees correct, in-order delivery of data running on top of the network layer service. The network layer is providing an unreliable datagram delivery service underneath. As I'm sure you can imagine, applications such as a web client or an email client find TCP very useful indeed. By employing TCP to make sure data is delivered correctly, they don't have to worry about implementing all of the mechanisms inside the application. They can take advantage of the huge effort that other developers have put into correctly implementing TCP over the years, and then reuse it to deliver data correctly. Reuse is a big advantage of layering. But not all applications need data to be delivered correctly. For example, if a video conference application is sending a snippet of video in a packet, there may be no point waiting for the packet to be retransmitted multiple times. Better to just move on. Some applications just don't need the TCP service. If an application doesn't need reliable delivery, it can use the much simpler UDP or User Datagram Protocol instead. UDP is an alternative transport layer that bundles up application data and hands it to the network layer for delivery to the other end. UDP offers no delivery guarantees at all. In other words, an application has the choice of at least two different transport layer services, TCP and UDP. There are in fact many other choices too, but these are the most commonly used transport layer services. Finally, we have the application layer at the top of the four-layer model. There are, of course, many thousands of applications using the internet. While each application is different, it can reuse the transport layer by using the well-defined API from the application layer to the TCP or UDP service beneath. As we saw in the last video, applications typically want a bidirectional, reliable byte stream between two endpoints. They can send whatever byte stream they want, and applications have their own protocol to define the syntax and semantics of data flowing between the two endpoints. For example, as we saw in the last video, when a web client requests a page from a web server, the web client sends a GET request. This is one of the commands of the Hypertext Transfer Protocol, or HTTP. HTTP dictates that the GET command is sent as an ASCII string along with the URL of the page being requested. As far as the application layer is concerned, the GET request is sent directly to its peer at the other end, the web server application. The application doesn't need to know how the data got there or how many times it needed to be retransmitted. At the web client, the application layer hands the GET request to the TCP layer, which provides the service of making sure it is reliably delivered. It does this using the services of the network layer, which in turn uses the services of the link layer. We say that each layer communicates with its peer layer. It's as if each layer is only communicating with the same layer at the other end of the link or internet, without regard for how the layer below gets the data there. Putting it all together then, network engineers find it convenient to arrange all the functions that make up the internet into layers. At the top is the application such as BitTorrent or Skype or the World Wide Web, which talks to its peer layer at the destination. When the application has data to send, it hands the data to the transport layer, which has the job of delivering the data, reliably or not, to the other end. The transport layer sends data to the other end by handing it to the network layer, which has the job of breaking the data into packets, each with the correct destination addressed. Finally, the packets are handed to the link layer, which has the responsibility of delivering the packet from one hop to the next along its path. The data makes its way hop by hop from one router to the next. The network layer forwards it to the next router one at a time until it reaches the destination. There, the data is passed up the layers until it reaches the application. So in summary, applications, bidirectional reliable byte stream between applications, typically, but not always, and they use application-specific semantics, which we'll be learning about later, such as HTTP or BitTorrent. The transport layer typically guarantees correct in-order delivery of data end-to-end and controls congestion, although some applications don't need this, and so they can use a different transport layer instead. The network layer delivers datagrams end-to-end. It's providing a best-effort delivery service with no guarantees. We must use the Internet Protocol. The link layer delivers data over a single link between an end host and a router, or between two routers. There's two extra things I'd like you to know. The first is that IP is often referred to as the thin waist of the Internet. This is because if we want to use the Internet, we have to use the Internet Protocol. We have no choice. But we have lots of choices for link layers. IP runs over many different link layers such as Ethernet, Wi-Fi, DSL, 3G cellular, and so on. And on top of the IP layer, we can choose between many different transport layers. We already heard about TCP and UDP. There's also RTP for real-time data and many others too. And of course, there are tens of thousands of different applications sitting on top. The second thing I want you to know is that in the 1980s, the International Standards Organization, or ISO, created a 7-layer model to represent any type of network. It was called the 7-layer Open Systems Interconnection, or OSI model. We don't need to spend any time on it in this course because it's been replaced by the 4-layer Internet model for all intents and purposes. But if you're interested, you'll find any networking textbook, and Wikipedia describes the 7 layers in lots and lots of detail. The 7-layer model defines layers that were combined in the 4-layer Internet model later. For example, what we call the link layer today was separated into the link layer that defined the framing format and the physical layer that defined things like the voltage levels on the cable or the physical dimensions of a connector. The network layer is pretty much the same in both models. The transport and applications layer is each represented by 2 layers in the OSI models. These are examples of commonly used Internet protocols. For example, HTTP, which passes most of its data in the protocol in ASCII, and how they map to the OSI numbering scheme. Today, the only real legacy of the 7-layer OSI model that you need to know about is the numbering system. You'll often hear network engineers refer to the network layer as Layer 3, even though it's the second layer up from the bottom in the Internet model. Similarly, you'll hear people refer to Ethernet as Layer 2, and you'll hear application referred to as Layer 7.